Hello friends, welcome to my lecture on first lecture on two-phase method. As an alternative to Bingham method, there is another method known as two-phase method to deal with linear programming problems. It involves involving artificial variables. Now, in this method the solution is obtained in two phases. In phase 1, all the artificial variables are eliminated from the basic variables. In phase 2, we use the solution from phase 1 as the initial basic feasible solution and use the simplex method to determine the optimal solution. So, we in phase 1 all the artificial variables are eliminated from the basic variables, and then the solution which we get in from phase 1, that is treated as initial basic feasible solution, and we use the simplex method to determine the optimal solution. So, in phase 1 what we do, let us consider step 1. After making all bi's positive, we convert each of the constants into equations by introducing slack, surplus and artificial variables. In step 2, we assign 0 coefficients to each of the primary, slack and surplus variables and the coefficient -1 to each of the artificial variables in the objective function. So, here in the in this method artificial variables are assigned the value -1. Each coefficient of the artificial variable is taken as -1. As a result, the new objective function is of the form z star equal to minus sum of artificial variables, because primary, slack and surplus variables are assigned value 0, okay, 0 coefficients they are assigned, but the artificial variables are assigned coefficient -1. So, when you write the new objective function, say it is z star, then it will be minus sum of artificial variables. Now, we maximize z star subject to the constants of the original problem using the simplex method, and then what we will have, 3 cases will be there. So, these cases are if maximum of z star is less than 0, if maximum of z star is less than 0 and at least one artificial variable appears in the optimum basis at a positive level, then the given problem does not possess any feasible solution. So, when maximum of z star is less than 0 and at least one artificial variable appears in the optimum basis at a positive level means the value, corresponding value in the B column is positive, then the problem does not possess any feasible solution. If maximum of z star is equal to 0 at least one artificial variable appears in the optimum basis at 0 level. 0 level means in the B column the value corresponding to the optimum artificial variable is 0, then we will proceed to phase 2. And in the third case, when maximum of z star is 0 and no artificial variable appears in the optimum basis, then also we proceed to phase 2. So, we proceed to phase 2 in 2 cases. The 2 cases are when the maximum value of z star is 0 and at least one artificial variable appears in the optimum basis at 0 level, or in the second case maximum value of z star is 0 and no artificial variable appears in the optimum basis. So, but in the third case, when maximum of z star is less than 0 and at least one artificial variable appears in the optimum basis at a positive level, then the problem does not possess any feasible solution. So, now let us go to phase 2. In phase 2, we start with the optimal solution contained in the final simplex table of phase 1. Okay. So, we will start with this final simplex table of phase 1. The solution we got there, that we will start with that. So, then we assign the actual cost to the variables in the objective function and a 0 cost to every surplus variable. Now, we eliminate the artificial variables which are non-basic at the end of phase 1. Okay. So, they will be eliminated artificial variables. Now, we remove Cj row values of the optimum table and replace them with Cj values of the original problem. Okay. Then we apply simplex algorithm to the problem contained in the new table to obtain the optimal solution. Now, what is the advantage of two-phase method over Bingham method? What is the advantage of two-phase method over Bingham method? We can always use Bingham method to check the existence of a feasible solution, but its computational procedure may be inconvenient because of the manipulation of the constant m. Two-phase method eliminates the artificial variables in the beginning. In the phase 1 itself, the artificial variables are eliminated. Now, when we solve the problem on a digital computer, we have to assign some numerical value to m, which must be larger than the values C1, C2 present in the objective function. But a computer can computer has only a fixed number of digits. Now, let us solve the following problem by using two-phase method. So, we have the problem minimum of z equal to 7.5 x 1 minus 3 x 2 subject to 3 x 1 minus x 2 minus x 3 greater than or equal to 3, x 1 minus x 2 plus x 3 greater than or equal to 2, x 1 x 2 x 3 greater than or equal to 0. So, let us see how we do this problem. So, first we will convert this minimization problem to maximization problem. Okay. So, step 1, express the problem in the standard form. Okay. Introducing the surplus variables, now we see this is greater than or equal to type, this is greater than or equal to type. So, we will have to add we will have to take 2 surplus variables and also 2 artificial variables. Okay. So, introducing surplus variables S1, S2, artificial variables A1, A2, the phase 1 problem in standard form becomes maximum of z star equal to, now we have 0 into x1, 0 into x2, 0 into x3, 0 into s1, 0 into s2, then a1 and a2. The coefficients of a1 and a2 are taken as minus 1 each. So, minus a1 minus a2 we have, and subject to now the questions that we have by using surplus and artificial variables are 3 x 1 minus x 2 minus x 3, then minus s 1 plus 0 s 2 plus a 1 plus 0 a 2 equal to 3, x 1 minus x 2 plus x 3, and then 0 s 1 minus s 2 plus 0 a 1 plus a 2 equal to 2, x 1 x 2 x 3 s 1 s 2 a 1 a 2 greater than or equal to 0. Now, we find an initial basic feasible solution. So, we have how many equations are there? We have 2 equations and the variables are 1, 2, 3, 4, 5, 6, 7. So, we have 7 variables and equations are 3. So, 5 variables can be taken as 0. So, we will take x 1, x 2, x 3, s 1, s 2 equal to 0 and we get the values of a 1 and a 2. Okay. A 1 comes out to be 3, okay, from here, and a 2 comes out to be 2 from here. So, x 1, x 2, x 3, s 1, s 2 and a 1, a 2 are all greater than or equal to 0, and z star comes out to be minus 5. Z star equal to x 1, x 2, x 3, s 1, s 2 are zeros, a 1 is 3, a 2 is 2. So, z star is equal to 5. Initial simplex table will be, now you see x 1, x 2, x 3, x 1, s 2, a 1, a 2, b column, okay, and then the basic variables are a 1, a 2, non basic variables are x 1, x 2, x 1, x 3 because they are assigned value 0 here, 0 in the objective function, okay, they are assigned 0, 0, 0, 0, 0, 0. So, we have 0, 0, 0, 0, 0, they are coefficients of x 1, x 2, x 3, s 1, s 2 in the objective function, and coefficient of a 1 and a 2 in the objective function are minus 1 each. Now, coefficient of a 1 in the objective function is minus 1, coefficient of a 2 in the objective function is minus 1, and this is your body matrix, okay, 3 minus 1 minus 1 minus 1, 3 minus 1 minus 1, 1 minus 1 1, minus 4 2 0, minus 4 4 minus, okay. So, this one these are the coefficients of x 1, 3 1 3 and 1, okay. The coefficients of x 1 are 3 and 1, coefficient of x 2 are minus 1 minus 1, coefficient of x 3 is minus 1 plus 1, okay, and these are the coefficients of s 1, s 2, coefficient of a 1 and coefficient of a 2, and these are b elements in the b column 3 and 2, this one 3 and 2, this one. Okay, so, these are coefficients in the b column. Now, we find zj star, c sigma cb aij. So, 3 minus 1 into 3 is minus 3, minus 1 into 1 is minus 1. So, total is minus 4, we subtract minus 4 from 0, we get 4 here, and then sigma similarly minus 1 into minus 1 is plus 1, minus 1 into minus 1 is plus 1, 1 and 1 is 2, 2 we subtract from 0, we get minus 2, and similarly we get zj star here as 0, here z star equal to 1, here 1, here minus 1, here minus 1, and here what we get, minus 1 into 3 is minus 3, minus 1 into 2 is minus 2. So, we get total minus 5. Okay. Now, Cj is equal to 4 here, okay. Cj is Cj minus Zj star. So, 0 minus 4 gives you 4, and 0 minus 2 gives you minus 2 here. This is 0, this is minus 1, 0, 0. Now, we can see that Cj is positive in this column. Okay. So, Cj is positive under x1 column, and therefore, this solution is not optimal. So, what we will do, this is our key column, okay, and we divide the elements of the B column by the corresponding elements of key column. So, 3 divided by 3 gives you 1, okay, and then 2 divided by 1 gives you 2. The minimum of 1 and 2 is 1. So, this is our key row, okay, and at the intersection of key row and key column we get key element. So, this is key element, 3 is the key element. Now, x1 is the incoming variable, a1 is the outgoing variable. So, here we will get in the next simplex table a1 will be replaced by x1 and this minus 1 will be replaced by 0, the coefficient of x1. So, we have this table, okay. X1 comes here, the coefficient of x1 is 0, 0 is there, okay, and then what we do, we divide the elements of key row by the key element, okay. So, 3 by 3 we divide all the elements of key row, okay. So, we get 1 here, minus 1 by 3, minus 1 by 3, minus 1 by 3, 0, 1 by 3, 0, and we get 1 here, okay. So, we get this 1, minus 1 by 3, minus 1 by 3, minus 1 by 3, 0, 1 by 3, 0, 1, okay. And then with the help of this row, this new row, okay, with the help of this new row, we make the element this element as 0, okay. So, what we will do? We make this element 0, okay. So, we have divided this row by 3, it became 1. So, now this is also 1. So, we simply have to subtract this new row that we have got this row from the second row, okay. So, what we will get? 1 we have 1 minus 1 we have this, okay, 1 minus 1 1 0 minus 1 0 1 and 2. From that we subtract this row and then we get this 0 minus 2 by 3 4 by 3 1 by 3 minus 1 by 3 1 1, okay. And then now we calculate Zj star. Zj star is 0 into 1 minus 1 into 0 is 0, 0 minus 0 is 0, then 0 into minus 1 by 3 minus 1 into minus 2 by 3 is 2 by 3, 0 minus 2 by 3 is minus 2 by 3. So, we get the new values of Cj are 0 minus 2 by 3, 4 by 3, 1 by 3, minus 1 by 3, 0, okay. And here Zj star is minus 1. Now, we can see Cj is positive under x3 column, okay, and s1 column, okay. So, maximum is 4 by 3, this is maximum, okay, 4 by 3. So, this is our key column, okay. So, now we have to find key row. So, divide minus 1 by 3, divide this 3, divide by 1 by minus 1 by 3, we get minus 3, and divide 1 by 4 by 3, we get 3 by 4. Minimum positive value we have to consider here in the theta column. So, minimum positive value is 3 by 4. So, this is our key row, okay. This is key row and this is key column. So, we have this as the key element, this is our key element, okay. Now, so what will happen? Now, x3 will come in and a2 will go out. So, instead of a2 now in the new table we will have x3, here the value in the CB column will be 0, okay. And what we will do then? This elements of the key row will then be divided by the key element, that is 4 by 3 to bring unity here. So, we have this row, this new table making key element 4 by 3 unity and replacing a2 by x3 we obtain the So, this is our x3 here, okay, this is x3, okay. So, we have 0 in the CB column, 0 for x1, 0 for x3, and we have here a1 okay. So, okay, right. So, what we have here now 4 by 3 be divided by 4 by 3 this elements of the key row, okay. So, minus 2 by this will remain 0, this will become minus 2 by 3 into 3 by 4. So, we get minus half. So, this element will become minus half, this element will become minus half, this will become 1, this will become 1 by 3 into 3 by 4, 1 by 4. Okay. So, we can see here minus half 1 by 4, okay, and this element will become what, minus 3 by 4, okay, minus 3 by 4, and this element will become 1 into 3 by 4. So, this will become 3 by 4, 3 by 4, okay. So, this will become 3 by 4 also, this one 3 by 4, and this is minus 1 by 4 in A1 column. In A1 column, yeah, minus 1 by 3, okay, divided by 4 by 3. So, we get 3 by 4. So, we get minus 1 by 4. So, new row that we get after dividing by 4 by 3, we get this like this. Okay. Now, what we will do, this element we have made 1, okay, by dividing by 4 by 3. Okay. Now, with the help of this one, okay, we make this 0 and this 0, okay, the other elements in the column corresponding to x 3, we make them as 0. So, this is minus 1 by 3, here we have 1. So, we multiply this by 1 by 3 and add to this row, okay. Here this is minus 4 by 3, here we have 1 by 3, 1. So, we multiply by 4 by 3 and add to this. So, we get this, okay, this is 0, this is 0, okay. So, after that what happens is, okay, so this we have made as 1, here we have minus 1 by 3. So, we multiply the elements of the key row by 1 by 3 and add to the above row. So, what we have? The above row is, you see, 1 minus 1 by 3, minus 1 by 3, okay, minus 1 by 3, and then we have 0, 1 by 3, and then we have 0, 1. This is the row, okay. 1 minus 1 by 3, minus 1 by 3, minus 1 by 3, 0, 1 by 3, 0, 1. Now, this row is what? 0, and what we have? A minus half 1, 1 by 4, minus 3 by 4, 1 by 4, minus 3 by 4, minus 1 by 4, and then 3 by 4, 3 by 4. Okay. Now, what we do with the help of this one, we make this element 0. Okay. So, we multiply this row by 1 by 3 and add to that row, okay, this row. So, what we will get? 1, 0 into 1 by 3, we add to this, it will remain 1. Then we multiply by 1 by 3 and add to that. So, minus 1 by 3, then we have minus 1 by 6. Okay. Then 1 by 3 we add to this, we get 0 here, and then we multiply by 1 by 3 and add there. So, minus 1 by 3 plus 1 by 12. Okay. That is what we get for this, and then we multiply by 1 by 3 and add there. So, we get 0 and minus 3 by 4 into 1 by 3. So, minus 1 by 4, and what we get here 1 by 3, we multiply by 1 by 3 and add. So, minus 1 by 12. Okay, then here we multiply by 1 by 3 and add. So, 0 and 1 by 4. Okay, and here we multiply by 1 by 3 and add. So, what we will get? 1 plus 3 by 4 into 1 by 3. So, that gives you 5 by 4. So, what will be the elements now? So, this will remain 1, then minus 1 by 3 minus 1 by 6. So, this is minus 3 by 6. Okay. Then we have 0, then here how much we have? Minus 4 by 12. So, minus 4 plus 1 minus 3 by 12. Okay. Here we get minus 1 by 4. Here we get this is how much? 3 by 12 minus 1 by 12. So, 2 by 12, and then we get 1 by 4, and then we get 5 by 4. So, what we get? 1 minus 1 by 2, 0 minus 1 by 4, minus 1 by 4, then 1 by 6, then 1 by 4, then 5 by 4. Okay, so this is what we get. Let us see what we are getting there. 1 minus half, 0 minus 1 by 4, 1 minus half, 0 minus 1 by 4, right, and then we get minus 1 by 4, 1 by 4, 1 by 4, 1 minus half, 0 minus 1 by 4, 1 minus half, 0, so this is there, this is there, this is there, this is there. Then what is the next element? Minus 1 by 4, 1 by 4, 1 by 4, 1 by 4, 1 by 4. So this should be 1 by 4. Okay, and then last one is how much? 5 by 4. So this is okay. Only we have this element we have to see. So 1, 2, 3, 4, 5, 6 element. So 1, 2, 3, 4, 5, 6. So here how much we have? 1 by 3 minus 1 by 12. So we get 4 by 12 minus 1 by 12. So we get 3 by 12. So this is 1 by 4. So this is 1 by 4, not 1 by 6. Okay, so we get this this row. Okay, 1 by, so we multiply it by 1 by 3 and add to the add to this row, add to this row. Okay, we get this row. And now let us find Zj star. Zj star is 0. Okay, Cj is 0, 0, 0, 0, 0, minus 1, minus 1. So Cj is less than or equal to 0 for all j, and therefore this table gives us optimal solution. And Z star, maximum of Z star is how much? This Z star. Okay, so maximum of Z star is also 0, because x1 is equal to 5 by 4, x3 is equal to 3 by 4. Okay, all other variables are non-basic variables. So that means x2 0, then we have s1 0, s2 0, and a1 a2 0. So in now maximum value of Z star. In Z star you take x1 as 5 by 4, x3 as 3 by 4, x2 s1 s2 a1 a2 equal to 0. What you get is 0, the value of Z star as 0. Now no artificial variable appears in the basis. Okay, no artificial variable, because the basis elements are x1 and x3. So no artificial variable appears in the basis, and therefore an optimal basic feasible solution to auxiliary problem and therefore to the original problem has been attained, because we have seen that when no artificial variable appears in the basis and Z star is 0, then an optimal basic feasible solution to the auxiliary problem and therefore to the original problem is obtained. Now let us consider phase 2. In phase 2, consider the actual cost associated with the original variables, and the objective function is then maximum of Z dash. Now Z dash is minus Z. Okay. So because we have the problem of minimization. Okay. So Z dash is minus of Z. So minus of 7.5 x1 plus 3 x2 we consider. So maximum value of minus Z we take. So maximum value of Z dash is maximum of minus 7.5 x1 plus 3 x2, 0 x3, 0 s1, 0 s2, 0 a1, 0 a2 subject to these constants 3 x1 minus x2 minus x3 minus s1 plus 0 s2 plus a1 plus 0 a2 equal to 3, and then x1 minus x2 plus x3 0 s1 minus s2 0 a1 plus 0 a2 equal to 2, and x1 x2 x3 s1 s2 a1 a2 greater than or equal to 0. Now the optimal initial basic feasible solution, okay, thus obtained will be an optimal basic feasible solution to the original LPP. So what we will do, the final table of phase 1 will become now the initial simplex table of phase 2. Okay. So basis is x1 x3, we can see x1 x3 is basis, okay, and the coefficient of x1 now, coefficient of x1 is minus 15 by 2. Okay. So we write there minus 15 by 2, coefficient of x3 here is 0. So we write 0 here, okay, and then we have 1 minus half, the same last table, 1 minus half 0 minus 1 by 4 minus 1 by 4. So we just copy that, you see here we just copy that, and then here x1, coefficient of x1 is minus 15 by 2, coefficient of x2 is 3, coefficient of x3 is 0, coefficient of s1 is 0, coefficient of s2 is 0, a1, a2 have been eliminated. Okay. Now, we find zj here, okay. Zj is minus 15 by 2 into 1 plus 0 into 0. So, minus 15 by 2, capital Cj therefore, is small cj minus zj gives you 0, and here we get minus 15 by 2 into minus 1 by 2 plus 0 into minus half gives zj as 15 by 4, then 3 minus 15 by 4 is minus 3 by 4. Here Cj comes out to be 0, here minus 15 by 8, here it is minus 15 by 8, and here what we get minus 15 by 2 into 5 by 8 plus 0 into 3 by 4, that is minus 75 by 8. Now, let us see Cj is 0 here, here negative, here 0, here negative, here negative. So, Cj is less than or equal to 0, and therefore, this solution is optimal. And so, an optimal basic feasible solution to the given problem is x1 equal to 5 by 4, x3 equal to 3 by 4, x2 equal to 0 because x2 is non-basic variable. So, x2 is 0 and minimum value of z. Okay. Now, this is minus 75 by 8. So, minimum value of z is equal to minus maximum value of your z dash, okay, which is minus 75 by 8, and we get 75 by 8. So, that is the minimum value of z. So, this is the solution to the linear programming problem. So, that is all in this lecture. Thank you very much for your attention.